In this introduction, I will explain to you what is the Bernoulli's theorem. Bernoulli's theorem is the relationship between pressure, velocity, and elevation in a moving fluid, liquid or gas, with negligible compressibility and viscosity, internal friction, and a steady or laminar flow. Daniel Bernoulli, a Swiss mathematician, presented this principle in his book Hydrodynamics in 1738, and this principle was named after him. Bernoulli's principle states that when the speed of a fluid increases, the pressure or potential energy of the fluid decreases, while the density and pressure are inversely proportional to one another. According to Bernoulli's principle, the sum of all mechanical energies in a steady flowing fluid, including kinetic energy, dynamic heat, fluid pressure, and potential energy, should be constant at all points of the flow. The equation of a steady flowing fluid of Bernoulli's theorem is given by P plus 1 over 2 rho V square plus rho GH equal to constant, where P is the pressure, rho is the fluid density, V is the fluid velocity, H is the relative height, and G is the acceleration due to gravity. The objective of this experiment are: first, to verify the validity of the Bernoulli's equation when it is applied to a steady flow of water. Second, to determine the relationship between the velocity of the water flow rate and the height of the water level. And last one is to verify the Bernoulli's equation.
The apparatus and equipment that we use in this experiment are water bottle, scissor and cutter knife, meter ruler, food container, and food color.
Today I will do experiment for Bernoulli principle. So let's start our experiment.
Before we start, we need to make a hole at each bottle by using knife cutter with diameter 0.3 cm and 0.6 cm. In the first experiment, we need to pour the solution water in the bottle with hole 0.3 cm, while close the hole with the thumb for the height 4 cm of the surface water from the hole. In the same time, release the thumb from the hole and start the timer. Next, quickly measure the distance of water from the bottle. Lastly, stop the timer immediately when the height of water reaches the hole. Then, repeat the experiment with the height of the surface water from the hole 8 cm, 12 cm, 16 cm, and 20 cm. For the experiment 2, we repeat the step in the first experiment by using the bottle with the diameter hole 0.6 cm.
For our discussion, based on the result in Table 1 and Table 2, during the diameter of the hole about 0.3 cm, as the height water from the hole increases from 4 cm to 20 cm, the time taken for the water to stop flow getting increases from 50.6 seconds to 141.23 seconds. In addition, the distance from the water travel from the bottle also getting increases from 5.87 cm to 14.8 cm. Next, during the diameter of the hole about 0.6 cm, as the height water from the hole increases from 4 cm to 20 cm, the time taken for the water to stop flow getting increases from 39.56 seconds to 113.75 seconds. Thus more, the distance from the water travel from the bottle also getting increases from 6.33 cm to 16.83 cm. From this observation, it's shown that as the diameter of the hole getting bigger, the time taken for the water to stop flow also being affected, as the time become more shorter. Also, the distance for the water travel also become more far. As Bernoulli principle state that as the speed of moving fluid increases, the pressure within the fluid decreases, causing the distance the water travel become shorter, and as the speed of the moving fluid decreases, the pressure within fluid increases, causing the distance the water travel become longer. Lastly, in order to achieve an accurate reading, the experiment is repeated about 3 times for each distance of height. Moreover, the eyes of the observer must be perpendicular to the reading scale of the ruler so that the result that we obtain is not defected.
As a conclusion, based on the experiment, we can conclude that the Bernoulli's principle is valid for flow as it obeys the theory as the smaller the diameter of hole, the longer the time taken, and the water travel further away too. This is because of the diameter of the hole affects the distance of the water travel from the hole, and this results to the longer time taken. From the graph obtained, show that the height of water from the hole is directly proportional to the time taken for each diameter. This same goes to the graph of height of water against distance between water and bottle. However, there are a few of errors during the experiments done. The first error might occur due to the parallax error in taking the reading of a ruler because the eye level is not perpendicular to the water travel on the ruler. Frictional loss existed since there is a contact between a fluid and the solid surface. Lastly, a patient is needed to run this experiment successfully. Thank you.